Recall the 8 definitions that I have defined in the previous video. So this is what I'm talking about. We'll be using this to prove. So in order to show that B minus A is the same as B intersect A complement, we'll have to show that B minus A is a subset of B intersect A complement, and B intersect A complement is a subset of B minus A. Let's firstly show that B minus A is a subset of B intersect A complement. So we're going to let X be an element of B minus A. If you can realize, B minus A is the difference, and by the difference definition, if X is an element of B minus A, means that X is an element of B and X is not in A. So since X is not in A, then X is in A complement by the complement definition. Hence X is in A complement and X is in B. And so X is in B intersect A complement by intersection definition. Therefore, X an element of B minus A implies X an element of B intersect A complement, which means B minus A is indeed a subset of B intersect A complement. Conversely, we'll have to show this. So since we want to show that B intersect A complement is a subset of B minus A, we'll let X be an element of B intersect A complement. Then X is in B and X is in A complement by the definition of intersection. Since X is in A complement, then X is not in A by the complement definition. And so X is an element of B minus A, since it's in B but not in A. This is by difference definition. Therefore, we have shown that if X is an element of B intersect A complement, then X is an element of B minus A. Meaning that B intersect A complement is also a subset of B minus A. Finally, we can agree that the two sets are equal. So that's how you prove it. Now let's move to this second one. A intersect B is empty if and only if A is a subset of B complement. So this one is biconditionally. We have to show if A intersect B is empty, then A is a subset of B complement. And also, if A is a subset of B complement, then A intersect B is empty. So let's start by showing that if A intersect B is empty, then A is a subset of B complement. Suppose A intersect B is empty, and let X be in A. So we'll have to show that X is in B complement in order to conclude that A is a subset of B complement. Now, since X is in A and A intersect B is empty, then X is not in B. Remember, X will only be in A intersect B if and only if X is in A and X is in B, else it's empty. That's why we said it's empty, because X is only in A but not in B. That's why we say that X has to not in B, then for this to be empty. So if X is not in B, then X is in B complement. So this tells us that if X is in A, it will be in B complement. So we use the preposition that A intersect B is empty, and we let X to be in A to show that X is in B complement. Hence, X an element of A will imply X an element of B complement, and we can conclude that indeed A is a subset of B complement if A intersect B is empty. Conversely, we'll have to show that if A is a subset of B complement, then A intersect B is empty. Suppose A is a subset of B complement and let X be in A. Then X is also in B complement since A is a subset of B complement. So since X is in B complement, it is not in B. And so X is not in A intersect B. Hence A intersect B is empty. So we have shown that these two statements are equivalent or they support each other. Moving to the third one. A intersect B is the same as A if and only if A is a subset of B. Meaning, if A intersect B is A, then A is a subset of B. And also, if A is a subset of B, A intersect B is A. We also have A or B is the same as B if and only if B complement is a subset of A complement. Meaning, if A union B is the same as B, then B complement is a subset of A complement. And also, if B complement is a subset of A complement, then A union B is the same as B. And also note that A is a subset of B if and only if B complement is a subset of A. So you can see it is clear that if A is a subset of B, then A intersect B is A and A union B is B. This proves that if A equals to B, A intersect B is the same as A union B. So let's only prove A and B and you'll do the rest as an exercise. Okay, doing this one first. A intersect B is A if and only if A is a subset of B. So as I said, we'll have to show that A intersect B is the same as A will imply A is a subset of B. Conversely, we'll have to show A is a subset of B will imply A intersect B is the same as A. Suppose A intersect B is the same as A and let X be in A. Now, if X is in A, and since we know that A intersect B is the same as A, then X is in A intersect B. And so, X is in A and X is in B. Hence, X is in B. And this tells us that X an element of A will imply X an element of B, meaning A is a subset of B. So, we have indeed confirmed that if A intersect B is A, then A is a subset of B. Conversely, we'll have to show if A is a subset of B, then A intersect B is equal to A. Suppose A is a subset of B and let X be an element of A intersect B. Then X is an element of A and X is an element of B. So we can see that X an element of A intersect B implies X an element of A. So A intersect B is a subset of A. Similarly, if X is an element of A, and since A is a subset of B, then X is also in B. So we have X contained in both A and B, which means X is in A intersect B. So A intersect B contain X if A contain X, meaning A is a subset of A intersect B. Therefore, if A is a subset of B, then A intersect B equals A. So simple as that. We are done with this one. So let's go to B. Now we'll have to show that A union B is the same as B if and only if B complement is the subset of A complement. So since it's biconditionally, we'll have to show that A union B is the same as B will imply B complement is a subset of A complement, and also B complement being a subset of A complement will imply A union B being the same as B. So I will only show one and leave the other as an exercise. Let's continue. Suppose A union B is the same as B, and let X be in B complement. Now, X an element of B complement will imply that X is not in B, and thus by complement definition, which will imply that X is not in A union B, since A union B is the same as B. So, if X is not in A union B, it's in the complement of A union B by the complement definition. So, X is in A complement and B complement by De Morgan's. So, X is indeed in A complement, and hence if A union B is equals to B, then B complement is a subset of A complement, because we have to show that if X is in B complement, it's also in A complement. So the converse part will be left as an exercise. So you'll take it from here back to here. Moving forward, let A, B, and C be sets. Then the following are true. If A is a subset of B, then A minus C is a subset of B minus C. If B is a subset of C, then A cross B is a subset of A cross C. For A not empty. If A cross C is the same as B cross C and C is not empty, then A equals to B. A cross into B minus C is the same as A cross B minus A cross C. A minus into B intersect C is the same as A minus B union A minus C. And A minus B minus C is the same as A minus C minus B minus C. So, we'll start by proving the first one. We'll prove them orderly as they appear. So, the first one, we're given our preposition that A is a subset of B. We have to conclude that A minus C is a subset of B minus C. So, suppose A is a subset of B, and let X be an element of A minus C. We want to show that X is also in B minus C in order to show that A minus C is a subset of B minus C if A is a subset of B. Now, X an element of A minus C will imply X is in A and X is not in C by difference definition. So since X is in A and A is a subset of B, then X is also in B. Hence, X is in B minus C. Because X is in B but still not in C. So it will be in the difference B minus C. Therefore, since X an element of A minus C will imply X an element of B minus C, we'll conclude that A minus C is a subset of B minus C, and we're done with the proof. So this is what I'm talking about. You're not guessing here, you see, we're using definitions. First thing first, you assume your preposition, then I let X be an element of A minus C. For me to show that A minus C is a subset of B minus C, if I let x to be an element of A minus C and show that x is in B minus C, then I can conclude that indeed A minus C is a subset of B minus C. And this is what I did. So this implies that x is in A and x is not in C by difference definition. Then I know that x is in A. So since x is in A and also A is a subset of B, then I can say x is in B. Then from there, I know that x is in B, but still x is not in C, then x will be in B minus C. Therefore, A minus C is a subset of B minus C. That's all.